we're getting to know our Laplace transform. We've seen its definition. The Laplace transform of a function is the integral e to the minus st times f of t dt. And we've looked at a couple of examples last time. So let's look at yet another one. So one more example for the moment. So an example of applying this definition, taking another standard function. So another standard function we can take is, what if we take the Laplace transform of an exponential itself? And the transform of this comes out in a nice way. So this is certain, exponential functions are important. They're useful for measuring kind of standard rates of decay or growth. They will feature in some of the ordinary differential equations that we want to be able to solve. Remember, this Laplace transform we're doing as a method that we're going to apply to differential equations to enable us to solve them. All that talk is yet to come. At the moment, we're just encountering the transform itself. And those ODEs will feature these exponential functions. So we need to be able to handle those and be able to take their transforms. Well, we can apply the definition. This is what the definition looks like. We just integrate the exponential e to the minus st featuring this new variable s multiplied by this function that we're taking the transform of. Well, the manipulation you're attempted to do on that is just to use the rules of exponents. You've got a product of two exponents there. So a product of two exponents is just a single exponent, and you add the exponent. So it's minus s plus a times t dt. Yeah. So it's just another integral of a single exponential, which doesn't really pose any problems. We can just go ahead and integrate it. It integrates to the same exponential, but rescaled to take account of that factor multiplying the t. So the integral looks like this, and if this comes to a finite value, then the integral exists, and we can say that the Laplace transform exists. Well, this is the limit as t goes to infinity of e to the minus s plus a t divided by minus s plus a. It's that limit that's evaluating at the top limit. And when you evaluate at t equals 0, you're just e to the 0. So it's just it's just 1. E to the 0, which is just 1. So, okay, this bit is easy to handle. This is just going to be 1 over s plus a. So the two minus signs will cancel. So it all comes down to the behavior of this limit. Okay, this bit at the bottom, okay, it's a limit as t goes to infinity. This bottom doesn't have any t, so it comes down to this exponential. Well, we've already discussed when you have e to some multiple of t, we already know the convergence. It's when the real part of this multiple times t, when that real part is bigger than 0. Then we'll be talking about e to some positive power of t, and that's going to converge to 0. So that will make the whole thing. This a up here, I should have said, is just some real parameter. So this is going to be equal to 0 plus 1 over s plus a, i.e. 1 over s plus a, when the real part of s plus a is bigger than 0. I.e. when the real part of an s is bigger than minus a. Okay, s is a real number, so the real part of s plus a is just the real part of s plus plus a. So when that's bigger than 0, just put the a over the other side. So it gives a similar kind of condition. Just when the real part of s is bigger than minus a, then this Laplace transform will exist. So there will exist this new function of s. This is what it will be. It's a kind of simpler function of s. 1 over s plus a. This is what the function will be. So that's another example. We saw that the Laplace transform was linear. Alpha f plus beta g, if you take its transform, it's alpha times the Laplace transform of f plus beta times the Laplace transform of g. That's our first basic property. First of our basic properties about the Laplace transform. It's a linear transformation. Extremely useful. If we ever want to transform some combination of functions in a linear combination, we just transform the individual functions and then make up the linear transformation again. Okay? So that's extremely useful. A second property is how to handle multiples of t. So this is another application of the Laplace transform, applying the definition of the Laplace transform in order to prove a property about it. Okay? It's a very basic idea. Taking the definition of something and working with the definition to extract general patterns of behavior out of it, general properties that it has. So what we're going to do here is we're going to suppose that the Laplace transform of f, some function f exists. So we'll suppose that the Laplace transform of a function little f is this function capital F of s. We've already seen a few examples. The constant function t, f of t equals t, this exponential function we've just done. But suppose we got any old function f with a certain Laplace transform. This is going to tell us what the Laplace transform of t times f of t is. Okay, so we're getting a new function, quite strongly related to the original function f, but this is the function you get when you multiply f of t by t. Adding in a factor of t. What effect does this have? Well, the theorem says it's minus the derivative of f with respect to s. So it's somehow the case that multiplying the original function by t is equivalent to differentiating the transform with respect to s and flipping the sign. Okay, this is a general pattern of behavior of the Laplace transform. And we'll be able to get a great application of it straight away. Remember, in a previous example, we've already proved that the Laplace transform of the function t was 1 over s squared. So once we know this theorem, that means I don't have to do another calculation to know what the Laplace transform of t squared is, or yet another integral to get the Laplace transform of t cubed, etc. Because I can generate t squared and t cubed, etc., just by multiplying t by extra copies of t. So I can just apply this result to generate those Laplace transforms. We'll see quite a good application of this result once we know it's true, once we've proved it with an application of the definition. Okay. But we're going to prove this one. We're going to start on the right-hand side. So minus df ds. Well, what is f? F f is the Laplace transform, which by definition is the integral e to the minus st times f of t dt. Yeah. So we're taking an s derivative of the integral. This is all in brackets. And what we can do here is interchange the two operations. So we can take the integral of the derivative of e to the minus st f of t and integrate it. So we can interchange the order of differentiation here, differentiation and integration. Now that mightn't be you mightn't universally be able to do that. There might be convergence issues to deal with, but we're not going to get bogged down in those technical matters. So assuming we can interchange these operations, the integration and the differentiation with respect to s, assuming we can interchange those operations. But once we do that, we can start to make progress then, because we have to take a derivative dds of this. Now the only place that the s appears is in the exponential. Yeah?
What minus f over ds equals minus dds of
Well, because this bracket here is what f is. F is the Laplace transform of little f. We assume that. Okay? And this in the brackets is the definition of the Laplace transform of f of t. Okay? The integral of the exponential times f. Okay? So we can actually carry that out because we're differentiating with respect to s, so we treat the other variable t as if it were just a constant. So the fact that this is a function of t here doesn't complicate it for us. It's just some constant multiplied by e to some constant times s. We can certainly differentiate an exponential with respect to s. Okay? Just e to some multiple of s. So how do you differentiate it? Well, it's differentiating this with respect to s. It's going to be minus t times e to the minus st times f of t dt. So that's just carrying out this differentiation. Differentiate that with respect to s. And then just tidy it up and repackage. You've got two minus signs there. They're going to cancel. Because this factor of minus 1 can go outside the integral. So that's going to go away. And then just move stuff around here and just emphasize it. It's e to the minus st multiplied by t f of t dt. Now, what are you looking at there on the last line? You're looking at an integral of the exponential e to the minus st multiplied by a certain function of t with respect to t. But that's just an instance of the definition of the Laplace transform. This is exactly the Laplace transform of t f of t. Because the Laplace transform of whatever is the integral of the exponential times whatever with respect to t. Yeah. So it's just the way these two operations interact. Multiplying the original function by t is the same as differentiating the original Laplace transform, f, capital F being the Laplace transform of little f. It's the same as taking the negative derivative of that f with respect to s. So that's another application of definition of the derivative to get a general property of how the Laplace transform behaves. Now we can immediately apply this. Okay? An application of this. previously, we saw that the Laplace transform of the function t was 1 over s squared. Right? And indeed, we saw the Laplace transform of the constant 1 was 1 over s. So what is the Laplace transform of t squared? And we make progress with that. Now we could, if we wanted to, just apply the definition for the Laplace transform, which is the integral 0 to infinity of e to the minus st times t squared dt. Then we'd be faced with an integral of t squared times an exponential, where we could either look it up, or using more basic properties, we could carry it out using the principle of integration by parts. But we don't have to go that deep because we've already got higher order results that will do it for us. We already know the Laplace transform of t. We know about this interaction between multiplying the original function by t and differentiating the Laplace transform. T squared is, after all, just t times t, isn't it? Yeah, so we can apply the previous result. The Laplace transform of t times t is just minus dds of the Laplace transform of t, i.e. minus dds of 1 over s squared. And what's that? Well, you differentiate 1 over s squared, you get minus 2 times 1 over s cubed. This extra minus sign changes it back to positive, so you get 2 over s cubed. So that was by theorem 2.2. We didn't have to go to the original definition of the transform. And we can use induction because, if we can get from t to t squared, well, then we can get from t squared to t cubed, then get from t cubed to t to the 4, and so on. So we can prove for all powers n, that the Laplace transform of t to the n is what? Well, what's it going to be? What's it going to be? The Laplace transform of t to the power n?
N over s to the n plus 1.
Not n, what's it at the top?
N minus 1.
So something to do with n, but what precisely?
N factorial.
N factorial. Yeah, n factorial. You see, because you pick up a 2 and you do t squared. When we get to t cubed, we're going to pick up a 3 by 2 in the numerator. Yeah.
Why?
Well, okay, we use this as our base case, yeah? So we went from t squared, we have to go from t up to t squared. So we have to differentiate 1 over s squared. And when you differentiate that, you get a factor of 2 in the numerator, don't you? To go to the next step, to go to t cubed, we're going to have to differentiate this. But when you differentiate this, the exponent 3 comes out, you get a factor of 3 in the numerator. You get a 3 by 2, which is 3 factorial. And when you go to t4, you have to differentiate the 1 over s to the 4, so you get another factor of 4 in the numerator. To keep generating the extra factors that generate all the factorial. So up here will be n factorial. So suddenly we know what the Laplace transform of any power of t is. So that was example 2.4. Another example 2.5, without any significant extra work, just putting together the results we already have, we can now say what the transform of any polynomial is. Say, I'll just give it some notation. What does a polynomial look like? It looks like, well, you're summing powers of t from 0 up to some order n, say, and you've got coefficients, say, alpha j. That's what a typical polynomial looks like. Yeah, so it's alpha n t to the n plus alpha n minus 1 t to the n minus 1, all the way down to alpha 1 t plus alpha 0. That's just a generic, typical, could be any polynomial. Right, for a choice of coefficients alpha and a choice of degree n. But we can immediately say what its Laplace transform is. What is it? In equation 2.15 at the bottom of page 44, I've messed up the notation there. Should be, yeah, just replace it with this. Replace it with this correctly written one. But you see, we already know what the Laplace transform of any power of t is. And a polynomial is just a big linear combination of powers of t. Isn't it? Alpha j change. See, alpha, it isn't just one alpha there. It's a whole collection of alphas. Alpha 0, alpha 1, alpha 2, all the way up as far as alpha n. So yeah, so I'm allowing the coefficient, you can put any coefficients you want on the powers of t. You get what I mean?
Yeah.
Yeah. So this could be any, this is a completely generic polynomial. It could have any degree, and it could have any set of coefficients. Yeah. So just by assigning values, you can build any polynomial out of that description. Yeah. Well, a polynomial is just a big linear combination. Take it that those alpha i's are all real numbers, or the alpha j are all reals. Then this is just going to be the same linear combination of the transforms of these individual ones. But we've already just seen how the transform of t to the j is j factorial over s to the j plus 1. Yeah. So it's not a polynomial, but something we, in general term, we can call a Laurent polynomial. So familiar with that phrase? Write it, a Laurent polynomial. So a Laurent polynomial is just a polynomial where you can have negative exponents. That's French accent for Laurent. A Laurent polynomial is just like a polynomial, except the exponents are allowed to be negative. When you say polynomial, we mean non-negative exponents on the variable. Yeah. But a Laurent polynomial can have negative exponents. So this is a Laurent polynomial in S. Okay. So what was the justification there? Well, that was just from this immediate result up here. Justification was this by applying previous results and linearity. So by taking the trouble to accumulate some well-chosen properties of the Laplace transform, we can immediately make like a lot of progress. We suddenly know now what the Laplace transform of any polynomial is. Okay? It's specified out of the ingredients of the polynomial. Now the next property is absolutely key. Absolutely key to the whole thing. So this is theorem 2.3. This is the transform of a derivative. I'll stick with the notation from the notes. Suppose x of t has a transform. So that integral of x of t exists. Okay. So this property is key. We suppose x has a linear transformation, and this is going to tell us about what the Laplace transform of the derivative of x is. Okay? So this is absolutely key to the grand project. Remember, the grand project is to be able to solve differential equations. Differential equations are things that feature some unknown function, which is normally a description of something through time, right? And the differential equation describes the interrelationship between the unknown thing and its derivatives. Its first derivative, its second derivative, its third derivative, going up to however many derivatives appear in the differential equation. And the primary key example of this is like classical laws of motion, Newton's laws of motion. So the position of something, its velocity, which is its first derivative of position, its acceleration, is its second derivative of position. These are all interrelated with the forces in action on the body. Okay, Newton's famous equation: the force is mass times the acceleration. Force experienced by a body is the mass of the body times the acceleration of the body. The acceleration is the second derivative of the thing's position. So the physical laws of motion and laws of other things in physics and engineering and biology and chemistry and science, very, very often, typically, the fundamental laws are to do with, give you a differential equation, okay, relating the unknown quantity and its derivatives, relating them together in some physical principle or chemistry principle, biological principle, etc. So remember, I motivated the whole thing by comparing with the use of logarithms to simplify calculations. So to work out a power, a to the power b is kind of hard if the a and b are awkward, if they're decimal numbers. It's not an easy calculation to work out the power. Well, you type it into the computer, but how does the computer do it? Okay, the computer doesn't have, computers are extremely stupid. Okay? It doesn't know anything of numbers to the power of other numbers. Okay? But mathematically, we know that if we take a logarithm of a power, it turns into a product. The logarithm of a to the power b is b times the logarithm of a. So if we could somehow know what the logarithm of a was, we'd have a simpler calculation to do. We just have to multiply its logarithm by something simpler than raising a power, and then use the inverse transformation, the exponential, to recover the original, the evaluation of the original power. Well, we're going to do a similar thing when faced with these ODEs. The transform we're going to use is not the logarithm, it's our Laplace transform. We're going to transform the whole equation, make it look different. We'll make it look different in a simpler way. And the transformed equation we're going to be able to solve using simpler principles, basically just algebraic manipulation. Algebraic manipulation to solve the transformed equation, get a solution to it, and then use the inverse Laplace transform to come back and recover the original unknown quantity x of t. The key to doing that is to know how to deal with derivatives of a function. So this theorem is telling us how they behave. And it says that the Laplace transform of the derivative is going to be s multiplied by whatever the Laplace transform of x of t is, minus the initial value of the function x. Okay, full stop. What this theorem is telling us is that there is a very strong, strict, well-defined relationship between the Laplace transform of x and the Laplace transform of its derivative. Okay? They are not two wildly different functions. There's an extremely strong connection. Whatever the Laplace transform of x is, the Laplace transform of its derivative is just s times the transform of x minus this constant. This is just going to be a number, x evaluated at t equals 0. So however complicated or awkward the Laplace transform of x is, the Laplace transform of its derivative is just a little bit more mixed up. It's just s times whatever the transform of x is minus this constant. Okay, so very exact relationship between the two. And we'll see in a moment, but it's not too surprising that this will generalize to the Laplace transform of a second derivative or a third derivative. So we can just apply it any number of times, just like we did for the Laplace transform of t to some power. Well, the Laplace transform of any higher order derivative, we can just iterate this result to get a set of results for all the different derivatives. And you'll notice that on the right-hand side, there's no differentiation involved. Okay, we got a derivative of x here, but over here, we don't have any differentiation. We just have this kind of algebraic operation of introducing a new factor of s and multiplying it by whatever function we have. So this, on the right-hand side, this looks kind of conceptually simpler thing to do than to differentiate the function. It's conceptually simpler of multiply by another factor of s and subtract a constant. And easier to conceive of than taking a derivative of the original function. So let's look at a proof of this. And there's no beating about the bush. It's just a direct proof from left to right. Using, again, applying the definition. So you can think of all of these as just applications of the definition and using our standard calculus techniques. Okay. So what is the Laplace transform of that? Well, you apply the definition. It's the integral from 0 to infinity, e to the minus st times this function, and this function is the derivative dx dt. So that's just by definition. Definition of the Laplace transform. Okay, we have to do this integral or do something to it. But this integral is screaming out at you. What's it screaming at you? I reckon why it's screaming so loud, it's disturbing me. It's telling you how to integrate it. It's already set up and prepared. But prepared for what? Process. Right? By parts. Be careful. These aren't fractions. We don't want to. Yeah, no. But it's set up for integration by parts because it's an integral of a function that's easy to handle. We can handle integrals and derivatives of the exponential function. It's an integral of this understood function times a derivative. But that's exactly how you set up and prepare things for integration by parts. The integral of, if you like, you probably remember it as the integral of u dv. Probably how you've learned it. It's the integral of a function times the derivative of something else. So this is prepared for NB. This is prepared for integration by parts. Remember when did I do the previous integration by parts? Morning, I did it. Just now. And this morning. Yeah, it was this morning. But in order to do my integration by parts, I prepared the thing. I prepared the integral like this. I rewrote the thing as the integral of something times the derivative of something else. So we proceed by integration by parts. We take the product of these two things, e to the minus st times x of t, evaluate that at 0 and infinity, and we subtract then the integral from 0 to infinity. But the second integral, you take this factor undifferentiated, so you take the x of t, then you multiply it by the derivative of that first factor. That's how you operate integration by parts. The derivative of that with respect to t is minus s e to the minus st, and that's all integrated with respect to t. So that's the application of integration by parts. So we just deal with the various bits here. So we got to evaluate the square bracket. Well, we can evaluate it at t equals 0 easily enough. When you evaluate it at t equals 0, you get minus e to the 0. E to the 0 is 1. And you get x of 0. So you get minus x of 0 there. In the front, you get the limit of this whole expression as t goes to infinity. But we assumed that x has a transform. So if x has a transform, it means that eventually x is dominated by some exponential. So x doesn't, it's not as if x explodes in value later on faster than some exponential. So we've assumed it is in effect dominated by some exponential. So this limit as t goes to infinity here will be 0. Because eventually this exponential is going to be increasing fast enough to drag this whole product down and make it converge to 0. So this will just have 0 quantity here, and you take the limit of this thing as t goes to infinity. So this is where we pick up the minus x0. Then you just inspect this integral here, and you notice it looks familiar. It's integral with respect to t. So this factor of minus s has no t in it, so it can migrate out to the front, right, by the linearity of integration. Because there's no t, just that this factor minus s can slide all the way out to the front. It doesn't depend on t. So it's minus minus s. So in other words, it's plus s. And what's left behind, we'll just change the positions now to make it look more familiar. It's the integral of this exponential e to the minus st multiplied by x of t. So in other words, it's exactly the Laplace transform of x of t. This integral is what you get when you apply the definition of L, the Laplace transform, to little x of t. Minus x0 plus the Laplace s times the Laplace transform of x of t. Okay, just by inspection, by reference back to the definition. Okay. So it's from the definition of L. Okay, and that's exactly what we were asked to prove. So this operation of differentiating the objective function is the same as multiplying the transform by s and shifting the whole thing by some constant. So we can keep going. Ask ourselves, what about the Laplace transform of a second derivative? What about that? Well, I could to try and repeat this argument. I could switch to the integral, the specific integral again. But so I'm lazy, so I avoid doing any integration if at all possible. Well, I don't have to do. I've already assembled enough properties of L. Because what is the second derivative? The second derivative is what? It's the first derivative of the first derivative. So it's d dt of dx dt. Agreed? That's true. The second derivative is just the derivative of the derivative. Well, hang on. We've just proved a property that tells us how to take the Laplace transform of a derivative of something, something being the x. So we just need to apply this now, where instead of x, we're thinking of dx dt. So just by immediately applying the theorem again, it's s times the Laplace transform of dx dt minus the derivative dx dt evaluated at t equals 0. Okay, so that's just applying the theorem. Then I'm faced with this thing, the Laplace transform of the derivative. I can apply the theorem again. That I've just proved that that's s times the Laplace transform of x at t minus the initial value of x. So I get this neat result that the Laplace transform is s squared times the Laplace transform of x, whatever that is. And typically, when we encounter these, I won't know that yet, because x is going to be the unknown thing in the differential equation. But the transform of the second derivative is going to be s squared times the transform of s of x minus s times the initial value of x minus the initial value of the first derivative of x. These constants in a typical physics type setup or typical time-based differential equation, these initial constants are often known to us as part of the setup of the problem. Because typically, we know the initial conditions of the model, and we're looking at how the model evolves over future time. Typically, we know where the quantity is located at time 0. We know what its velocity is at time 0. And the differential equation describes how that thing will evolve over time. So very often, these initial values come to you as part of the setup of the problem. So the known initial conditions of it. And again, the way to think about this result is the transform is doing some simplifying work. So rather than thinking about the second derivative of some unknown thing, you can instead just think of the quantity s squared times some unknown function, minus s times a constant minus another constant. Conceptually, algebraically, these are easier operations to handle with and work with on the right-hand side compared with taking a second derivative. And can keep going to find nice expressions, nice expression for the Laplace transform of any order derivative of x with respect to t. And typically, we'll only need ones for the first, second, and maybe third derivative. Because for most applications, those are the kind of derivatives that you encounter in the differential equations. But that's so see the corollary on page 45 for that. So that corollary is just proved by using induction and theorem 2.3. So what we've seen there is a gathering together of three very important properties of the transform. It's linear, how it behaves when you multiply the objective function by t, and how it behaves when you differentiate the objective function. And so that's the key step. This is the thing that allows us to make progress with working with the differential equation. Okay, that the transform of a derivative behaves in a nice, well understood way. So that's the thing we're going to see being applied. That's the thing we're going to see that conceptually simplifies the differential equations and allows us to solve it. So we'll continue with this next week. We've got a good set of exercises that we can work with there in exercises 2.1 in the tutorials this week. Okay. So I'll see some of you in the tutorial and the rest of you in lectures next week.